Okay, hi everybody. I'm Roland Farrell. I'm a postdoc at Caltech. Today I'll be telling you about some work on hadron dynamics in the Schwinger model. So this is kind of another one of these high energy physics applications. We've heard a couple of great talks previously. This will be another example of how we're able to use IBM's quantum computers to start probing interesting things relevant to high energy physics. As an outline for this talk, I'll start by providing some motivation and background. Some of it's going to overlap with what was discussed in the previous talks, but hopefully it'll be a slightly different take, and maybe you can get something else from it. Then I'll tell you about some tricks that we did in order to be able to perform these efficient simulations of hadron dynamics. In particular, we really cared about having scalable methods that would allow us to go to this utility scale where we're doing simulations on 100 plus qubits. And I think a lot of these kind of methods and way of thinking about the problems can be pretty universal and hopefully could be applied in other contexts. And then finally, I will share the results from quantum simulations of these hadron dynamics using IBM's quantum computer, IBM Torino. Okay, so to start off with something that hopefully all of us are familiar with, the matter around us is primarily composed of atoms. And in atoms, we have a nucleus with protons and neutrons that are surrounded by a cloud of electrons. And this is what makes up everyday matter. And if you could zoom in really, really close on an electron, you would still see an electron. By this, we kind of mean that electrons are fundamental particles. We think they're really this kind of emergent blob of energy that comes out of the quantum field theory describing electrodynamics. But it's something where there's no substructure. We really believe an electron is an electron. But it turns out it's not the case for the things inside of the nucleus. So here, if you were able to zoom in really close on a neutron or a proton, you would find that actually they have substructure. And this is the realm of the quarks and the gluons that make up these neutrons and protons. These are described by quantum chromodynamics, and we have kind of a complete model for how the quarks and gluons behave. Actually, more generally, these bound states of quarks and gluons can be more exotic than neutrons and protons. And kind of the umbrella term for them is these hadrons. And the simulations that I'll be discussing is kind of hadrons in a simplified model looking at their dynamics with an eventual hopeful connection to these bound states of quarks and gluons. So why do we care about hadron dynamics? Well, one of the key challenges in high energy physics is kind of predicting these dynamics from first principles. So there's kind of many questions that we wish to solve, which we cannot currently solve. One of them is looking at these particle abundances that occur in very high energy collisions, such as you get at the LHC. So here you would collide like two heavy nuclei together, like lead. And remember, each of these nuclei are composed of these quarks and gluons. When you smash them together at high enough energy, they actually break free of these neutrons and protons and form this exotic phase of matter called the quark-gluon plasma. And it's kind of an outstanding theoretical challenge to understand how does this quark-gluon plasma form, how does it eventually cool and produce additional hadrons. This really requires simulating this fundamental strong nuclear force in very out-of-equilibrium scenarios. It's something that we want to be able to know to understand the strong nuclear force better, but also we're using these high-energy particle collisions to probe new physics, so we would really like to have a very good understanding of what our current models of physics should be predicting. So this is one application. Another application would be looking at transport properties in ultra-dense matter. So for example, in certain extreme astrophysical environments, like in neutron stars, you can have matter that gets squeezed so closely together that actually it really is described more by these quark and gluon degrees of freedom than the neutrons and protons. And we want to be able to understand how does charge transport in this very dense situation? How does heat transport? This is important for understanding, for example, how neutron stars cool. But to solve all of these requires working really from first principles. And to do that, we need to work with the strong nuclear force quantum chromodynamics. So we had some good introductions on this previously, but kind of the short summary is that quantum chromodynamics is this quantum field theory that describes how these quarks and gluons interact and behave. And we think that we have the equations that describe quantum chromodynamics, but we don't know how to solve them. They're kind of too complicated. But one of the great realizations is that we don't actually need to solve them. Instead, we can simulate them if we had a powerful enough computer, or in this case, if we had a powerful enough quantum computer. This is going under the umbrella of quantum simulations, where we believe that we could actually simulate these dynamics by emulating these interactions on a very controllable quantum device. So that provides kind of the motivation for this work. This explains what hadrons are and why we're interested in their dynamics. Next, I want to introduce the specific model that we worked in and tell you about the tricks that we employed to actually do these utility scale simulations. So the model we looked at is this lattice Schwinger model. So this lattice Schwinger model, it's a 1D model on a lattice where you have fermions, in this case electrons and positrons, and they're interacting via the electrodynamic force. So you can think of them as exchanging photons. And the reason this is a very popular model to study is it turns out that it's a very kind of nice simplified model of quantum chromodynamics, this theory governing the strong nuclear force. In particular, one of the properties that will be important for us is that if we ask what are the low energy excited states of this system, they turn out to be these hadronic-like objects that are composite of electrons and positrons. So if you look at the excitations, they're not these fundamental degrees of freedom of the fermions. They're actually these composite bound states, which we will call hadrons. Now, to actually run this on a quantum computer, we need to take our theory of one-dimensional fermions and map it onto something that looks like a spin chain. And here we have a very nice Jordan-Wigner mapping that allows us to map fermionic operators onto spin operators. And so we can equivalently think of this as being a bunch of qubits with some interactions between them governed by some Hamiltonian. One thing I want to emphasize is the nature of these interactions. So in 1D, you can think of this as like a generalization of the Coulomb interaction. So in 3 dimensions, maybe we remember that the potential between two charges falls off like 1 over r, where r is the distance between them. You can think of this by imagining kind of like a sphere of electric flux line and thinking about how many of those flux lines hit the charges as you move them further apart. It turns out in 1D, any flux line will hit any other charge, and from this you can deduce that actually this potential energy grows linearly with the separation. So instead of decreasing, it actually gets stronger as you pull them apart. Kind of in equations, it will look something like this, where your potential energy or your interaction term looks like a sum of different pieces where you're evaluating the charges on different sites, and there's a coefficient between them that depends on their separation. And because this energy grows as you pull the charges apart, this is what causes the charges to be confined. So if you pull them apart far enough, eventually it'll be more energetically favorable to pop these new particles out of the vacuum, which then screens the charges and leads to this confined phase and these hadrons. So this is the Schwinger model. Our quantum simulation will have 2 steps. First, we will prepare in our case, a hadronic excitation, and then we will do time evolution to study its dynamics. So the state preparation has 2 parts. First, we want to prepare the ground state, or this quantum vacuum everywhere, and then we want to excite a hadron. And I'll briefly touch on some ideas that we had for doing both of these. So for the ground state, we kind of took this ADAPT VQE protocol, which was designed for preparing ground states in quantum chemistry, and generalized it to our application with this SC ADAPT VQE. So the methodology here is that we have some variational quantum circuit, so it depends on some parameters. But the ansatz is designed in such a way that it's a scalable ansatz. So what this means is that if you kind of determine this quantum circuit that prepares the ground state on a small system classically, we have a way to extrapolate the circuit to prepare the ground state on a much larger system. And this really has 2 different parts. So the first part is our system has this translation symmetry. So the Hamiltonian is translationally invariant. And we also have localized correlations in this model. And so combined, this gives us scalable circuits. Essentially, you can think of these quantum circuits as finding a way to build out these correlations over a correlation length. And then due to the translation symmetry, we can kind of stitch together a bunch of the different pieces to build the ground state on as large of a system as we want. This is emphasized with this plot here showing one of the variational parameters in our circuit ansatz, this theta 1, as a function of system size n. And you see that it really lies on a nice exponential curve. We kind of have a good theoretical understanding for why this convergence should be exponential. And this allows us to extrapolate well beyond 28 qubits. In our case, we need to extrapolate all the way to 112 to do our quantum simulations, but this is no problem. This is how we're able to scalably prepare the ground state. The next step is to take the ground state and then apply some excitation operator to excite a single hadron on top of it. And here we did a very similar thing. So we kind of tuned this excitation operator on small systems classically. So this excitation operator acts on a handful of states, and we tune that operator to have maximum overlap with just these single hadron states. And once we tune this operator, it turns out that after we've prepared the ground state, we can kind of act with this operator on a much bigger state, and it's still going to prepare these single hadrons that we're after. So this tackles the problem of state preparation. The second step is the time evolution. And again, it naturally breaks into two different parts. So our Hamiltonian is a sum of essentially free fermion components, and then another term which is this Coulomb-like interaction. So the free fermion, this is relatively simple. If we look at the Hamiltonian, it has these single z terms, and then it has this xx, missing a plus sign, but it's supposed to be xx plus yy. This allows the fermions to hop from one site to the other. And it's kind of known how you would convert a trotter step of this into a circuit. It looks something like this, has a very nice brick wall structure. The important thing is that if we asked how many depth do we have per trotter step, it's only 4. So we could imagine doing on the order of 20 plus steps before we run into kind of overwhelmed by noise on the device. But the much bigger issue is thinking now about these interactions. So when we do this Jordan-Wigner mapping, our fermionic interaction now has terms that look like this. So we have essentially ZZ interactions between all qubits that are weighted by the separation between the qubits R. And this is really problematic because you can immediately see this has order n squared terms. And so the depth, if we wanted to trotterize this, would at least scale linearly with n, and we'd quickly be in a regime where we cannot scale this to a very large system. To make matters even worse, there's interactions between kind of qubit 0 and qubit 111 on this 1D chain. These are very long-range interactions that are not natively supported on the heavy hex architecture. So we'd have to do a lot of swap gates in order to engineer these long-range interactions. So both of these combined kind of made it so that, okay, there's no way we're going to be able to do scalable dynamics. So we really had to think hard about how to circumvent this. And what we realized is that there's kind of a non-perturbative process at play here, which dynamically screens these charges, essentially due to confinement. So even though this interaction kind of naively looks like it grows stronger and stronger as you go to larger and larger distances, if you're only ever concerned about low energy states that are confined, it turns out that everything gets screened. And so if you have two charges and they go beyond the screening radius, then actually this interaction becomes quite weak. This is shown in a little cartoon here, showing these correlations between charges as a function of their separation. And you can see there's this nice exponential decay. This is kind of a property of being in this confined phase. So this immediately motivated, well, why don't we just truncate the range of these interactions beyond the screening radius? This will be an exponentially good approximation, and it's going to help us solve a lot of the problems that we had before. So whoops, not the laser pointer. So if we had the full interaction, if we look at the qubit coupling map, we'd see everything is coupled to everything else. This is not going to work. But after doing this truncation, we see that in our case, we only need to consider interactions up to next to nearest neighbor. So it's still a pretty long-range interaction, but it's one that we were able to do without too much trouble on the quantum computer. So this is how we managed to do these long-range interactions. So these are these two tricks for doing efficient simulations. Now I want to present the results from actually running this on the quantum computer. So from a high level, our quantum simulations look like the following. We start by preparing this Hadron using this scalable circuits ADAPT VQE protocol. So the circuit looks like this. You prepare the ground state. Then you act with this local Hadron excitation operator. You can think of the state being produced as being this collection of single hadrons that's smeared over a handful of lattice sites here. Then after preparing this state, we're going to time evolve. So we're going to act with a bunch of trotter steps, and as we do this, our initial hadronic excitation is going to spread out. So in the previous talk, Nikita talked about preparing these wave packets that were able to travel coherently. This was done a year previous to that, where we didn't know how to make good wave packets. So we weren't able to have kind of resolved momentum. And because of this, our state that we initially produced could travel in both directions. So you'll see that as you time evolve, they kind of move back to back. There's kind of a 50% chance that it moves right, 50% chance that it moves left. And we're just doing more time evolution with this truncated interaction. So once we reach our target time, then we'll measure all the qubits. In particular, we'll measure this particle density, which is going to let us see this hadron dynamics in real time. OK, so with that, I'd like to show our results from the device. So these were run on IBM Torino. What this plot is showing is as a function of lattice site, which you can think of as qubit. So this was run on 112 qubits. On the vertical axis is showing the simulation time. And the colors indicate this particle density. On the left side of this plot is a noiseless simulation using matrix product state. On the right side of the plot is the results from IBM Torino. And one thing that we know because of the symmetries of our problem is that if we didn't have any errors, this would be a completely reflection symmetric figure. But we do have errors. So on the MPS side, you can see that initially we have this hadronic excitation that creates some particles, and then it starts to propagate outwards like this. On the quantum side, we see similar behavior, but as we get to later times, we're running deeper circuits, we start to see that kind of this coherent propagation fades away and kind of crumbles into something that looks like the vacuum. At the same time, we know that we're evolving regions that look like the ground state. They shouldn't evolve, but due to noise, we can see noise is kind of creating these particle-antiparticle pairs, and so it shows up as little kind of speckles on this diagram. But excitingly, we're able to actually see this hadron propagation, at least kind of initial signatures of it. And one of the really shocking things is we were able to run circuits with almost 14,000 2-qubit gates and depths approaching 400. So initially, we were just planning on doing this simulation kind of like one time step at a time, and maybe we would get to time equals 4. But then we got to time equals 4, and stuff looked pretty good, so we just kind of like kept going further and further until eventually it kind of broke, but we were able to make it to t equals 14, and we were very, very kind of shocked at how well the IBM device was able to perform. And the reason why we were able to extract such good results was because we really took a lot of statistics that allowed us to do very aggressive error mitigation. So in particular, over this whole simulation, we took 154 million shots. And from this, we were able to really kind of prune out runs that looked like they had errors and really focus on the ones that seemed to be the most noiseless. So to talk about the error mitigation a little bit more, we did a few different things. Some of them have been talked previously. This dynamical decoupling. We did the readout mitigation with M3. We did polytwirling to shape this noise channel. We also used this ODR, or operator decoherence renormalization. Then we were able to do some symmetry averaging. But it's kind of cool to see the effects of all the different error mitigation on the results. And that's what's shown over here. So what I was plotting on the previous slide was this vacuum subtracted quantity. Here it's kind of this column minus this column equals this column. And what I was showing previously was the fully mitigated results, which is shown in this bottom right-hand corner. But you can see initially, if you look at the raw data, it's very hard to discern any signal kind of with your naked eye. It's consistent with 1, which is the fully depolarized value. And if you're looking at this, you would just kind of throw up your hands and say, OK, there's no signal there. We need to go back to earlier times. But actually, after doing these various stages of error mitigation and really trusting the process, you can see this signal emerge. And finally, at the end, we're able to see the shape of this hadron as it's moving outwards. One thing I want to stress is that these error mitigation methods, while kind of empirically useful, do have inherent bias. And so if I had to zoom in here, you would see that there are systematic errors between where these points lie and the MPS prediction. And so in the future, we kind of want to explore these more sophisticated error mitigation methods, which maybe have a higher sample overhead, but actually are guaranteed to not be biased. So with that, I'd like to wrap up. I'd like to thank IBM for inviting me to give this talk and organizing such a wonderful conference. I'd like to thank all of you for your attention and thank my collaborators on this work, Mark Ia, Anthony Ciavarella, and Martin Savage. If you're interested in this work and it's a topic of one of these challenges, you can find more details in these two papers that are published and shown down here. So with that, I'd like to thank you all.